Hello, welcome to the third and final video in the gas carb oil quench heat treatment modeling tutorial series for an axisymmetric part. In the two previous videos, we built a gas carburizing model and a thermal model to look at the carbon profile, microstructure, and hardness of the part based on the heat treatment recipe we simulated. In this video, we are going to convert the thermal model into a stress model using the DANTE Model Builder so that we can see the approximate stress and deformation that the part goes through during the heat treatment process. Before we get started building the model, let's open up Abaqus CAE from our working directory. I'm going to copy the path, change the directory, and open up Abaqus CAE. Now that we have Abaqus CAE open, I'm going to select Standard/Explicit Model, go to File, Open, and select the CAE file that we saved from our previous videos. This CAE file contains our carburizing and thermal model that we built previously. Since we already have the carburizing and thermal model built with the DANTE Model Builder, all we have to do now is build the stress model. To build the stress model, we're going to be using a different technique in comparison to the carburizing and thermal model. First, we can go to Plugins, open up the DANTE Model Builder, change our active model to AXI_T, or the thermal model, and click Convert to Stress. Using this technique, we automatically copy over some of the necessary information from the thermal model that we need, such as the material, the step information including the step time and incrementation, as well as the temperature history, which we will need to drive the stress model. Once we click Convert to Stress, we can close out of the DANTE Model Builder, and it takes us to the Mesh module. Inside the Mesh module, we're going to have to change the element type from the thermal heat transfer element type to the axisymmetric element type. To do this, we can go to Mesh, Element Type, select our entire part, click Done, and instead of heat transfer, we're going to be using axisymmetric stress. Once we selected axisymmetric stress, we can uncheck Reduced Integration and click OK. Once we've changed the element type, the next thing we'll have to do is create our nodal set for the stress model. To do this, we can go to the Assembly module, go to Tools, Set, Manager, and click Create. This nodal set will contain the node that we're going to use to fix the axisymmetric part in our assembly environment. Since this is an axisymmetric part and not a 3D part, the only axis or direction that we have to fix is the y-axis, so our part doesn't fly away. So to do that, first we can give a name. I'm going to call this y_fixed. Select node, click Continue, and select the very bottom left node here that we're going to use to fix the part. Although the location of the node that we select doesn't matter, it is good practice to select the node that can be more easily interpreted during post-processing. The reason for this is our reference node, and we'll have a displacement of 0. This means that the rest of the part will grow and shrink relative to the node that we fix here. If we select a node in the inside of the part, for example, although the results won't be incorrect, the results might be harder to interpret based on the location we select. After we selected the fixed node that we're going to use, we can click Dismiss, go to Plugins, and open up the DANTE Model Builder back up. The next thing that we'll have to do is make sure that our stress model is our currently active model and fix our Y node that we just created. To do this, we can go to Initial/Boundary Conditions and click Add Displacement Boundary Condition. In Abaqus, typically the 1, 2, and 3 direction correspond to the X, Y, and Z axis. Since we want to fix the Y-axis in this case, we're going to select U2 and change our node set from the all node set that's selected currently to the Y-fix node that we just created. Next, we can click Apply, Dismiss, and close out of this window. After we added the displacement boundary condition, we can save our CAE. Next, we can go back to the Models page and click Submit Job. That's all we really have to do for the stress model, so make sure we change the element type and add the boundary condition to fix the part in the environment. Once we've submitted the job, we can go back to our working directory here, scroll down to our stress files, so the underscore S, and wait for the .sta file or status file to appear to make sure our analysis is currently running. So if we give this a second here, we can see that the .sta file appears in our folder, and let's double click this. So again, our STA file holds the information at our monitor node that we selected in our thermal and carburizing model. For a carburizing model, the monitor node outputs the carbon content. For a thermal model, the monitor node outputs the temperature history. But for a stress model, it outputs the displacement at the node we selected. Since step 1, we start at room temperature at 20 degrees, we can see that the displacement is basically 0. And since step 1 is our heating step, if we scroll down to the end of the step, we'll notice that the displacement is slowly increasing due to the thermal expansion. We can reload this file, scroll down to the very bottom, and we see that our analysis has completed successfully. So we can close out of that .sta file, go back to our Abaqus CAE, close our DANTE Model Builder, go to the visualization module, and load in our ODB file here. Once I have my ODB file loaded in, the first thing I want to do is click Plot Contour on both shapes here. And we can select the first option here, Plot Contours on Deformed Shape. To make the contour a little bit more easy to read, we can go to Options, Common, select Feature Edges for visible edges, which gets rid of the mesh on the inside here. And we can give a uniform deformation factor here. For this instance, for this part, we can use 25. Once we have those options selected, we can select NT11 inside our variables. This is to make sure that the temperature history was imported correctly into the stress model. So if we go to Frame Selector and go to the very beginning of the analysis, we can see that our initial temperature here is a uniform 20 degrees, which is correct. So this represents the room temperature of the part before it enters the furnace for carburizing. As we go through each increment, we can see that the temperature of a part is slowly increasing until we get to about a temperature of 900 degrees, which is our carburizing temperature. So step 2 is our carbon mapping step. We maintain a temperature of 900 degrees, and at the end of the carbon mapping step, we go into our quench. So once we're in the quench step, we can see that the temperature on the surface here is decreasing. This is based on the ambient temperature of 50 degrees for the oil quench that we used and the oil quench HTC that we applied in the thermal model. So if we go through each increment, let's go to the end of the quench step. The temperature reaches about 50 degrees Celsius, which is correct. And last but not least, we can take a look at the air cool step. So again, the air cool step, we gave an ambient temperature of about 20 degrees and used the air cool HTC values applied to the exposed surface on all 4 edges of the part. So at the end of the air cool step, so after 7200 seconds, the part goes back down to a uniform 20 degrees for room temperature again. So the temperature history seems to be loaded in correctly. Next, we can take a look at the S, or the stress values. The first stress value that we can take a look at is the S11 stress value. So 1 corresponds to the X. So for an axisymmetric part, the S11 represents the normal stress in the X direction, or the radial stress in this case. For a DANTE analysis, the stress values, the units that we use for stress, are megapascals. So we have a maximum value of 527 megapascals and a minimum of negative 447 megapascals. So the positive 527 here represents a tensile stress, and the negative represents compression. For this specific heat treatment process, we can see that the surface here, the top and bottom of the part, is in compression at about 446 megapascals, while right below the surface, this red contour here, we have tensile stress at about 527 megapascals. The next stress value we can take a look at is the S22 stress value. So S22 represents the stress in the Y direction. For this axisymmetric part, for this ring slice, this will be the axial or longitudinal stress. If we zoom in a little bit, again, we have a maximum tensile stress of about 627 megapascals and a compression of about 450 megapascals. So the 450 megapascals in compression we can see on the inner diameter surface and outer diameter surface of the part here. The compression would be right below the tensile surface to balance out the stress on the surface here. On the inner diameter, we have about a tensile stress of about 627 megapascals, and a tensile stress on the outer diameter right below the surface here of about 447, so a little bit less. Next, we can take a look at the S33 direction. So S33 represents the Z direction. For this axisymmetric part, this would represent the circumferential or hoop stress that the part experiences at the end of the process. Again, we can see that the outside of the part here on the exposed surface, it's all in compression at about 458 megapascals with a little bit of the tension stress right below the surface, especially at the corners here on the outer diameter side. So the tensile stress is about 533 megapascals, while the compression is about 458 megapascals on the surface. Next, we can take a look at the U. So the U will be the displacement or distortion of the part. For U, we only have two options to take a look at. One is the U1 and the other one is the U2. So U1 represents the displacement in the X direction, and U2 would obviously represent the displacement in the Y direction. For displacement, one thing you can do is select plot contours, hold it down, and select plot contours on both shapes. So this way we can compare the final shape to the original shape that we used before the heat treatment process. For the distortion in the U1 direction or the X direction, we can see that the part grows horizontally at about 0.002. So for DANTE, the units for displacement is millimeters. So this part grows about 0.002 horizontally here, and grows in the negative X direction about 0.0048. The next variable we can take a look at is the U2 direction. So again, similar to the U1, this is just the displacement, but in the Y direction this time. And since we fixed the part at the very bottom left node, the value here at this node should be 0, or a reference node in this case. In the U2 direction, we can see that the part expands vertically and has a little bit of expansion below the original shape too. If we increase the magnification or the deformation scale here to a value such as 100, we can increase the magnification to see the effects of the heat treatment on the distortion of the part throughout the process. So if we go back to the beginning of the heating process, let's change this back to 25. We can see the part go through thermal expansion here. With a little bit of shrinkage here as the part goes through austenite transformation. All the way into the quench step. So once we're in the quench step, we should see the part start shrinking. So one is due to the thermal expansion effect, due to quenching, or thermal shrinkage, and the other one would be due to the phase transformation to martensite. So if we scroll up in our variables here and take a look at the volume fraction of the martensite, we can see martensite starting to form here, especially right below the surface here, below the carburized case. So if we go back to U, so once the part starts transforming the martensite, we see a little bit of growth. And finally shrinkage back to the original deformed shape after the heat treatment process. Thank you for tuning in to our final video in our gas carb oil quench tutorial series for an axisymmetric part. If you have any questions regarding the heat treatment process or modeling using the DANTE software, you can visit our website at www.dante-solutions.com or email us at support@dante-solutions.com. Thank you.